Hello friends, welcome back to our channel. So in today's session, we'll discuss about one more concept in discrete mathematics, that too in the recurrence relation, that is a higher order linear homogeneous recurrence relation. So in our previous session, we have seen the first order homogeneous recurrence relations and second order homogeneous recurrence relations, and now we'll go with the higher order recurrence relations. So without delay, we'll start our session. So higher order homogeneous recurrence relations. So in today's session, we'll discuss about the introduction, that means how to solve the higher order homogeneous recurrence relations, and in our next session we'll see an example problems how to solve the higher order. So first of all, what is this higher order? So we have studied or we have discussed about the first order and the second order. If any recurrence relation was given, so how to find the order means the difference between the highest subscript and the lowest subscript, that we have discussed. So with respect to that particular formula, we are going to find out the order of any homogeneous recurrence relation. So higher order means the current term will depend on more than two previous terms. So if the current term depends upon one previous term, then we calling it as a first order recurrence relation. And if the current term depends on the previous two terms, then we are calling it as a second order recurrence relations. And if the current term depends on more than two previous terms, more than two previous terms, then we call it as a higher order. That so this may be third order, fourth order, fifth order, and so on. Okay, so first order, if it is a first order, we are having only one root, only one root. Coming to the second order, if it is a second order, it will be having two roots, and if it is a third order, obviously it will be having three roots. If it is fourth order, four roots, and so on. So the higher order can be any one among these things. Okay, the first order, second order, and the higher order, we are calling it as a higher order. So whatever the steps we have discussed while solving the second order will be similar for the third order and remaining orders also. So we'll be mainly concentrate on this third order. Okay, third order. So what is the first step? We need to find whether the given recurrence relation is in a third order or not. How can we find? So obviously it should depends upon previous three terms, as well as the n value should be greater than or equal to 3. Then only we can say it is a third order. So if it is a third order recurrence relation, then the second step is we need to form an auxiliary equation. So all the steps are same. Okay, all the steps are same. So mainly now I am considering the third order. I'm teaching you about the third order homogeneous recurrence relation. So even though it is a third order, it will be calling it as a higher order. Okay, now the first step, check and make the recurrence relation. I am using RR, recurrence relation, into third order. Okay, that means n should be greater than or equal to 3. N should be greater than or equal to 3. Now the second step, find auxiliary equation. So how to find the auxiliary equation? Let it be the relation is in the form Cnan plus Cn minus 1 An minus 1 plus Cn minus 2 An minus 2 plus Cn minus 3 An minus 3 is equal to 0, because the current term, okay, this current term, or you can also use in this way, okay, the current term will be depending upon previous three terms, where c1 cn minus 1 cn minus 2 cn minus 3 all are constants. So simply we can replace cn with k cube. So if it is a third order, the k will be cube. Thus n is the highest order, right? So among all these subscripts, n is the highest order. So for that we have to use a k cube. If it is a fourth order, it will be k power 4. If it is a fifth order, k power 5, and decrease. So cn minus 1 is equal to k square. Cn minus 2 is equal to k power 1. Cn minus 3 is equal to k power 0. So the equation can be written, auxiliary equation can be written as Cn k cube plus Cn minus 1 k square plus Cn minus 2 k plus Cn minus 3 is equal to 0. So C1, Cn, Cn minus 1, Cn minus 2, Cn minus 3 are all constants. So from the given relation, we have to find out the constants and we have to apply the k value. So where k is the roots. Okay, k is nothing but a roots. So if it is a third order, we will be having a 3 roots. If it is a fourth order, we will be having a 4 roots. Now we are focusing on the third order. So k, we will be getting 3 roots. So this is the auxiliary equation. What's the next step? We need to find roots for auxiliary equation. Auxiliary equation. So whereas Cn, Cn minus 1, Cn minus 2, etc., all are constants and k are auxiliary, roots. So we'll be having 3 roots, k1, k2, k3 are roots. Okay, k1, k2, k3 are roots. So now here we will be having 3 cases. Okay, if roots are real, if roots are if roots are distinct or equal or real and imaginary, similar to our second order. So what is the general solution for these 3 cases? Now I am arranging this one, right? First step, second step, third step. Now we are having a k1, k2, k3 values. Now we need to find the general solution. So what is the general solution? Okay. So case 1. What is the case 1? Roots k1, k2, k3 are distinct. Distinct means different. Okay. All the 3 roots are different. If all the 3 roots are different, then the general solution will be an is equal to capital A k1 power n plus capital B k2 power n plus capital C k3 power n. Okay, so where k1, k2, k3 are roots and A, B, C are constants. So this is for third order. This is for third order. If suppose we are having a fourth order recurrence relation, then the general solution will be in the same way: a k1 power n plus b k2 power n plus c k3 power n plus d k4 power n, if it is a fourth order. Similarly, if it is a fifth order, then it will be having 5 roots. So all, along with this particular expression, so one more root will be added. So e into k5 power n. So this is for third order and this is for fourth order, and it will be keep on going. Okay, and see, I'm erasing this one. Hope you understood. So the same formula you can apply for any order. Okay, any order. Now, case 2. So what is a case 2? Case 2 means roots k1, k2, k3 are equal. If all the three roots are equal, then the general solution is an is equal to a plus bn plus cn square into k power n. Okay, so this is the formula for third order. Then what about if it is a fourth order? An is equal to a plus bn plus cn square plus dn cube into k power n. So this is for fourth order. For fifth order, there will be one more quotient, that is e into n power 4. So the same thing applied for different orders, higher order. So we are calling it as a higher order. So I am erasing this one. Next, case 3. Roots are real and imaginary. Okay, real and imaginary. If roots are real and imaginary, then the general solution will be an is equal to a into k1 power n plus r power n into c1 cos n theta plus c2 sin n theta. Okay, so where k2 is equal to k3 is equal to r is equal to root of p square plus q square, and theta is equal to tan inverse of q by p. So this is the formula. So here, if the roots are real and imaginary, if one root is we are getting one root and the two roots are imaginary. So imaginary means p plus or minus I into q. Okay, p plus or minus I into q. So then p square plus q square will become r, and k1 power n, and theta is equal to tan inverse qp. And if we are getting four roots, among four roots, if two roots are equal, then this will become this formula. Okay, if two roots are equal. So hope you understood this one. Case 1, case 2. Okay, so which we have discussed in our second order recurrence relation also. So case 1, case 2. Now coming to the case 3. So if it is a fourth order and fifth order, automatically one more term will be keep on adding. Coming to this case 3, this is for third order. Okay, what we have written is for third order. And if it is for fourth order, so case 3, fourth order. Fourth order means we'll be having k1, k2, k3, k4. 4 roots. Okay, 4 roots. So if we are having a 4 roots and 2 are equal, so if k1, k2 are equal, and k3 and k4 are p plus iq, then the formula will be an is equal to, both are equal. So if both are equal, we know the formula a plus bn into k power n plus r power n into c1 cos n theta plus c2 sin n theta, and the remaining are same. Kr is equal to k2 and k3, k3 and k4, which is nothing but p square minus q square. and theta is equal to tan inverse q by p. Okay, so this is one. Now one more question, if both are different, k1 and k2 are different, okay, if k1 and k2 are different, so remember all these formulas, simple. So I'm arranging this one. Okay, if both are different, okay, case 3, this is also case 3. Okay, fourth order, k1, k2, k3 and k4. So k1 not equal to k2 and k3 and k4 is equal to p plus iq. If the roots are in this way, okay, if roots are in this way, then the formula will be an is equal to, both are different, so we know the formula for if roots are different, a into k1 power n plus b into k2 power n plus r power n into c1 cos n theta plus c2 sin n theta, where r is equal to k2 k k3 k4 is equal to root of p square plus q square, and theta is equal to tan inverse of q by p. So this is the formula to find the general solution. So there are a lot of cases. So we have, if you understood the second order, how to solve the second order recurrence relation, then automatically you can able to solve any order recurrence relations. So third order, fourth order, fifth order. So based upon the same formula, we are deriving the remaining orders also. Right? So hope you understood. So I'll stop here. This is for third order and the fourth order. Okay, so just remember the formulas. So in our further sessions, we'll solve a few examples on these higher order homogeneous recurrence relations. Right? Yes, I'll stop here, and please visit the previous sessions, that is how to solve the first order and particularly how to solve the second order homogeneous recurrence relations. And remember once again, all these formulas will be suitable to solve the homogeneous recurrence relation. If the recurrence relation is a non-homogeneous, these formulas are not suitable, not sufficient. These formulas will be suitable but not sufficient. Okay, so yes, so let's stop here, and if you have any doubts regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.